Am I recording? Am I recording? Am I recording? I am recording. Okie dokie. So now we're going to dive into content. Talk about current electricity. And I think I might actually switch up the order that we do these in. I ran low on time for one of the important examples in the 3 o'clock class. So I think I want to front load it with the definitional stuff. Then we're going to come back and apply the definitions and make sure that we have plenty of time for that. Okay. First off, drawing. We're going to spend a minute drawing. Stupidly, not that there are no standards, there are like 5 competing standards. I'm going to show you my way of drawing that I will always sketch. Uniformly, I promise. The textbook does not follow my drawing conventions. I'm sorry. And the homework system is based off the textbook. If you look on YouTube videos, you'll probably run into other conventions there. It's annoying as all get out. I'm just as annoyed as you are, trust me. Here is how I will always draw a resistor. Come on. Okay, he was paired. And there we go. Okay, here's how I will always draw a resistor. Come on. Why can I not draw on this? Does anyone know why you might not be able to draw? No, there I could draw. There we go. It's just I don't know. Whatever. There's a resistor. There should be sharp lines. Let me try that again. I want to make this nice. There, that's better. 3 ups, 3 downs. If you put 4, I'll give you a passing grade, but then I'll kill your pets. Stupidly, the textbook puts 4. I'm sorry. This way is prettier, objectively. A battery. Let's see. This is the battery. This is a cell. Double A's aren't actually batteries. You know that? You have a double A, a triple A. Those are cells. Put more than one of them together, multiple cells make up the battery. A 9-volt is a battery. Your car battery is a battery. Battery is there are multiple cells in series which make up the total battery. A little bit of trivia for your pub night, you know. Copies that are 21. I'm going to ignore that distinction and I'll now call this a battery, which is abusing terminology, but this is faster to draw. Very importantly, you must know that the longer line is positive because sometimes textbooks, online resources, whatever, will omit the plus sign. The plus sign is the longer side of the battery is the positive voltage end. Junction. Even the examples that I lifted out of the textbook to show you in the next couple of slides don't do this. I want you to do this because in my experience, this really helps when learning Kirchhoff's current law. This is a junction. This is not a junction. A junction is where multiple wires come together and touch. Aw, how touching. This is a vertical wire and a horizontal wire passing through each other, not touching. This and this. Your textbook is only going to have wires near each other if they touch. The homework system is. I want you to be precise. Anytime there's more than 2 wires, anytime there are 2 lines that are meeting, anytime there are more than 2 lines meeting, I want you to draw a big fat dot on it. We call this a node, a junction, an intersection, I think those are the terms that I usually use to refer to them. A place where wires meet. Okay, is good? Any questions with the drawing? Hey, real fast. What does a resistor hold constant? What is always true about a resistor? It has a constant what? Resistance. What is true about a battery? It holds a constant what? Voltage. What does a junction always have constant? Nothing. It's just wires. Okay, I'm going to come back to Kirchhoff's laws. Yeah, I think next time I write these slides, I'm going to do them all in different order. Kirchhoff's laws are going to be tools for analyzing the circuits. Here are two definitions you can get down pretty damn fast. Series means connected with no junction. Parallel means connected at both sides. So again, you must be able to know, recognize, define, identify. Series means their components are connected with no choice. Electricity leaving one has to flow into the other. Who plays Dungeons and Dragons? Nerds. Okay. Series is a bad dungeon master. Series is a railroaded plot. You leave one adventure, you're on to the next one, no choices. You've seen this in video games too, right? Video games that you have no choice but to go on to the next mission. Parallel is a Bethesda game. Any Fallout New Vegas players here? Very parallel. Any Baldur's Gate players here? Very parallel. Very importantly, parallel has to start at the same point and end at the same point. They have to meet at both places directly. Only like 5% of you play D&D, really? Okay. Thought you guys were nerds. Series or parallel, what do you see? Parallel, they're touching at the tops, they're touching at the bottoms. By the way, three things can all be in parallel. You can have three things in series. It doesn't have to be just two. Series or parallel, what do you see? All three series, there's no junctions, there's no, I mean, there are places where two wires meet, but there's no choice, there's no place for it to go on to a third place. Series or parallel? All series. Let me get one more. Doesn't matter what's in the box. Series and parallel aren't words for resistors. Series and parallel are words for any components. My iPad does not like this pencil. I don't know why they're complaining. Maybe it's notability. Okay, your task real fast is to identify a series, two components that are in series. Turn to your neighbor and discuss. A, B, C, D, and E. What components are in series? Oh, let's put it in the Google form. Question me in the Google form. Tell me some components that are in series. Parallel are relationships between components or groups of components. Okay. No, just series. Just tell me series and E. Why so serious? Again, from O to everyone, the question is, in question E in the Google form, tell me some components that are in series with each other. Any two components that are in series. Or three. Maybe there are three things that are in series with each other. Yeah, the bottom of C is connected. If this weren't connected, C wouldn't actually be part of the circuit. B is connected, yeah. The wire D is connected, yeah. That wire isn't a lie. The cake is a lie, but that wire is a lie. Yo, I have an answer. Two proposed connected to each other are both very parallel. There's no other way to have. You got three more components? Okay, 10 seconds. Talk to neighbor, discuss real fast. I want to see everyone respond. Oh, I need to make, these are junctions. I'm violating my own thing here.
There's no junction, but between B and E there is. Even though it's a straight line. I want to say.
Okay, time's up. Correct answer is A and B only. Look at E's left side. E's left side is not connected to anything in series. Everything it's connected to has multiple junctions. E's right side is not connected to anything in series because everything is touching A, C, and D has junctions. It's connected to three components, not one. A and B are touching each other and their junction has no third place that's going out. A and B are touching, right? But that point doesn't touch anything else. That's series. Again, especially if you got this wrong, write this down. Series, they're touching. Where they touch has nothing else touching it. They're monogamous. Upon the definition of parallel, can you find parallel combination or more than one? Oh, now it's working normally. What the hell? You're just screwing around with me? No, it's like you were screwing around with me. I didn't think you were doing it. I mean, one of my biggest convictions after getting a PhD in physics and spending a lot of quality time with equipment is that devices are actually sentient and they like fucking with us. Such a cleaner diagram. Ready? Put her in. Show what you got. What's in parallel? No, not the definition. Give me examples of what is in parallel with what. A and B are in series with each other. The AB combination is in parallel with itself, but A is not in parallel with anything. B is not in parallel with anything. Only AB together, glomped into a single thing, is in parallel.
Oh. Would you write that as like so one zero? Yes. So would I have to combine one more to say?
If they're combinable components. Okay, and the answer for this, C, D, and E are in parallel. That's it. A is not in parallel with anything. B is not in parallel with anything. C, D, and E are all in parallel with each other. You could say that A, B combined together, the combination of A and B is itself in parallel with things. But I want you to know to say that AB is in parallel with C does not mean that A is in parallel with C and B is in parallel with C. It means if I had an equivalent component that replaced both A and B, that single component would indeed be parallel with the other. You could say C, D, E, and the AB combination are in parallel, but do not tell me that A is in parallel with nada. Do not tell me that B is in parallel with nada. There is a trick for finding parallels. Follow along. This could be useful. Shade or color your wires. Colors. Okay, I like colors. No, not delete. It's screwing with me. It's screwing with me. It just likes to screw with me. Okay. Okay, so shade or color your wires. I have the ability to color here, at least for a time, so let's color my wires. Everything connected with wire is colored the same color. If you've got if you've only got one kind of pencil, then make, I don't know, right crosshatches along one wire, and little circles or bubbles along another wire, and straight lines across a third wire, or just make a super bold fourth wire, whatever. Everything connected with wire has to have the same color or symbol. Okay, now I've got a blue line. All these components are connected with blue line, 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 blue line. And the last conductor I see. Come on, punk. Everything else is green. Okay, in terms of colors, things are in series if and only if they share a color and nothing else shares that color. A and B both have red on them and nothing else has red, therefore A and B are in series. Things are in parallel if and only if they have the same pair of colors. C and D and E all have green to blue. B does not have green on it. A does not have blue on it. So A and B are not in parallel. The AB combination, though, the AB combination goes from green to blue. So if we talk about AB as a single component, and we will eventually do this, AB as a single component does go green to blue. For now, though, I want you to be able to identify which individuals are connected in series or which individuals are in parallel. Yeah, does this help? Okay. Turn to your neighbor and discuss for 2 seconds. And I want a question, and then we'll move into the hard stuff. Okay, ask me a question. Please. If D and E were connected, how?
Like you erase the L on the side. Like
You mean if I did this? And directly hook them up to each other where? The bottom of D to the right side of E or what? Okay, how geometrically lines are drawn has no effect on circuit operation. It's all about what end is connected to what end. If the one side of D is connected to the one side of E and the other side of D is connected to the side of E, it doesn't matter how the symbols are arranged, that's still parallel.
What is the blue line? Like,
One of the wires connecting B, C, D, and E.
so they're not a series or a parallel?
A wire is never in series or in parallel. Series and parallel are words that describe relationships between components. Like, I don't know, siblings and cousins. A person can't just be sibling. Sibling is a relationship. Two people can be siblings of each other. I'm not just cousin. I have a cousin relationship with 6 people in the world. But a person is not just cousin or not cousin. Cousin is a word that describes a relationship. Okay, good. Now let's get crazy. Wait, last chance, last chance. Anything about these fundamentals? Everything we're doing builds on this. Yeah, let's go crazy. It's not actually that cray-cray. What we're doing now is called Kirchhoff's laws, and lesson 1, which drives me nuts. So please feel free to drive me nuts, sir. There's not far to go. This is not a cha sound. He's German. So it's funner to say than Kirchhoff. Kirchhoff is for peasants. Kirchhoff. 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 Kirchhoff's laws, not Kirchhoff. Kirchhoff. Okay, so that very important lesson aside. Gustav Kirchhoff. It's fun, you can spit on the person you're talking to. Kirchhoff. Gustav Kirchhoff realized 2 very important things about circuits. 1, charge is conserved, 2, energy is conserved. Duh! Charge is stuff. Stuff that doesn't appear, stuff that doesn't disappear, stuff that doesn't teleport. Right? Energy is conserved. You may have heard that rumor in your chemistry classes, right? The fixed amount of it. What goes in must come out, energy-wise, of the circuit or whatever, of anything. Okay, now Kirchhoff was a physicist, so of course he made these more complicated. Get it. Let's apply these principles to electricity. In electricity, if you look at any point, any node, any junction, any place in the circuit where wires meet, current approaching that junction must equal the same amount of current leaving that junction. Again, current is stuff. What goes in has got to come out of any node. Energy is conserved. If I go around a complete path, come back to my starting point, what I've gained energy-wise must be balanced by what I've lost energy-wise. These statements are equations in disguise. What I'm going to do is I'm going to take a circuit and I'm going to analyze it. I'm going to write these down as equations. I'm going to say, I'm going to have a left-hand side equals I in and the right-hand side equals I out. I in better equal I out from a node. I'm going to draw a loop around the circuit and I'm going to say around this path, V up equals V down, V gained equals V lost. It'll be an equation. And the point will be, you'll be able to solve it unknowns this way. Now I'm going to give you a series of trace circuits that get increasingly complicateder. And you can guess at the beginning, probably, but we're going to show how these apply, how you can apply Kirchhoff's laws to them. The goal here is to understand Kirchhoff at a deeper level, because we're going to apply Kirchhoff to things that you can't do simply later on. Okay. Oh, I want to make a note here. A student after 3 o'clock asked me, last week's homework you covered this week, what gives? The answer is that's going to be happening for a month. We're going to be covering the same devices, resistors, batteries, wires, adding a couple here and there. But every week we're going to develop more powerful tools for understanding them more deeply. So what you're about to see momentarily will make what you did last week seem easy. That's the whole thing. The things that are on this week's homework and quiz you'll be struggling with next week, God willing, the tools that you develop will make what's hard this week easy next week. So don't be mad at me. I can't just teach you everything everywhere all at once. I wish I could. We're introducing stuff and then making it easier and easier as you get more and more familiar with it. Okay. That's it. First off, I want to give you a chance to try this on your own. For the sake of time, let's be snappy about it. Question G, give this a shot, see what you could do. What is the battery voltage given this information? Question G, give it your best shot. More like my drawings. Good, Sabrina. Good, Nobu. Sammy, good job. Brandon, good job. Pat your back on yourself, Stephen. Nargis, you got it. Jacqueline, oh yeah, lots of correct answers. Good. Angelique, almost my favorite number, but no. Nope. We're going to talk about that in detail momentarily. The answer is really, or wants to pose a lot. But the current disco pose a question. The resistor will always pose in time with the input. Battery may or may not get the proposed current. Normally, this battery, when there's only one battery in the circuit, current will flow from the negative end to the positive end of the battery, and from the positive end back to the negative end. We'll make that more sophisticated in a second. And then later when we get to inductors, we'll make it so sophisticated you'll want to try it. But yeah, here's the first one. Okay, time's up. Put your best shot in. That's a lot of correct answers. Good, good, good. Correct answer is 24 volts. Now let's use this to practice Kirchhoff's law. First off, what does the current law tell me in a series circuit must be true? What goes in must come out. Do you see any junctions? I mean, in a sense, there are three junctions. There are three places where components meet. I claim that Kirchhoff's series law, the current law, tells me that the current entering this wire must be the current exiting this wire. Whatever leaves this resistor has got to be into this battery. Whatever leaves this battery must go into this resistor. What goes out of this resistor must go into this resistor. Current in series is constant. Always the same, identical electron. That's an important principle. That tells me the current in the 10 ohm resistor. What is the current in the 10 ohm? 0.6 amps. How do you know? I told you the current in the 30 ohm resistor. Where did those 0.6 amps come from? Right? You see? Okay. Very importantly, are there 0.6 or are there 1.2 amps being provided by the battery? Who thinks 0.6? Who thinks 1.2? Who's asleep? You get it. No. People who didn't vote, no. Come on, give it a shot. Let's see again. 0.6. Who buys the 0.6? Who buys the 1.2? Correct answer is 0.6. Remember what current is. It's a rate of passing of stuff. The battery can't be providing electrons faster than they are leaving through the resistors. Story time. Here's an elevator. It takes people from ground floor up to the 40th floor of the building. Here's a 10th floor water slide. Here's a 30th floor water slide. If I were an architect, buildings, you would only get down from upper levels by water slide. Especially if I'm designing for a lawyer's office. Screw them suits. Okay? So as current flows around, let's imagine that 600 lawyers per day go into the elevator to go up to the top floor of the building, right? 600 lawyers go uphill, go up to the higher level of the building. 600 lawyers per day had better darn well be passing through the first water slide to get down to the middle of the building. 600 lawyers per day had better darn well be going down that, right? What the rate at which charges are going uphill and the rate at which the charges are going to the next components, it's all one building, it's all one path. They better be going around. What going up must be coming down in terms of the particles and the rate at which they're going. Make sense? Hey, by the way, there's another connection here that I can make, another analogy I can make. Where you are in the building is your voltage. A battery supplies energy. Remember potential energy equation? What's potential energy? Gravitational potential energy is mgh, mg times height. Height is very analogous to voltage in a circuit. I am driven uphill by a battery, just like an elevator takes me uphill. Hey, does the electricity want to go up, by the way? Do the lawyers naturally fly up to the 40th floor of the building? No, it takes an energy source. What's the energy source in a building? Some things electricity better be provided to the motor in the elevator, right? The elevator doesn't naturally carry its load up to the upper floor of the building. A battery has chemical energy being turned into electrical energy to drive those charges up voltage. The electrons don't naturally flow up voltage. The charges don't naturally flow to higher voltage. Charges will naturally flow down voltage. You're at some voltage here. That current will flow to a lower voltage here, will flow to a lower voltage here. That's the negative terminal of the battery, as low voltage as you can get. Think about this. You'll need this for the next problem. Current naturally flows from high voltage to low voltage. Okay, now let's solve the problem. Those are the points that I could juice out of this. We actually have to solve the problem. We get that 24 volts. Here's how you do it. What's the voltage when 0.6 amperes flows through 30 ohms? What's the equation? V equals IR. What's I times R? Current times resistance. In this case, 30 times 0.6 is 18. What does that mean? Does that mean that the battery voltage is 18 volts? IR tells you the voltage across that resistor. 0.6 times 30 is 118 volts difference from here to here. What's I here? 0.6 amps. What's its R? So its V is 0.6 times 10. It goes by the other name of 6. 6 what? Does that mean the battery voltage is 6? Means the difference in voltage from one side of the resistor to the other is 6. So I would say this has an 18 volt difference across it. This has a 6 volt difference across it. Is that energy being given or taken from electrical form in those resistors? What do you think? Do resistors give circuits energy or do they take energy from electricity? They take. Resistors turn electrical energy into heat energy. That's it. You may have noticed this in the lab. If you used a low ohmage resistor, you might have noticed it gets hot. Right? You saw that? You saw that. Test the resistor and noticed it was warm. Okay. So the resistors are losers. The battery is a supply. Our law, the voltage law, says go in a circle, and the source of voltage must be balanced by the losses of voltage. I just lost 6 and I lost 18. How much did I start with? 24. Turn to your neighbor and express. What did I just say and why did I say it? Wire resistance is very, very, very small. So any battery is going to supply very, very, very large current through it. Large current, small resistance, a lot of power.
So technically through the battery, connect them to, zero case wire.
Then the extremely low resistance outside the battery can reveal the inside the battery resistance. Well, not resistance for the physical resistor filter to it, but chemistry, its own resistance. These are the reactions, oil, the reactants. And we're going to get a very hot battery, possibly an explosive battery. If you short a high enough voltage battery, if you take a wrench and connect it across the terminals of your car battery, you're going to see a very, very hot sulfuric acid coming in from that battery. Good way to lose your eyesight and or light. I don't know. But I would never want to try the experiment. Follow-up questions on this one. Again, this illustrates the current law in that the current everywhere is the same. It's all the same 0.6 volts. Amps. You cannot do this problem without recognizing that the 0.6 amperes of flow in this resistor is the same 0.6 amps as in this. As is the same 0.6 amperes flowing through this, for that matter. As the same 0.6 is flowing through this lower wire. It's all 0.6 amps in this series circuit. Once you know that, you can recognize V equals IR tells you the voltage here and the voltage here. 6 volts, 18 volts. Voltage law says what goes up must come down energy-wise, voltage-wise. So if I lose 6 and I lose 18, I must have started with 24. Battery voltage, 24 volts. Yeah? Great, now let's make it harder. I'm going to give you a second battery. This one is considerably harder. I think I'm going to walk you through it directly rather than throw you at it. 20% of the first class, 20% of the 3 o'clock section got this. I don't know how many of them just guessed. I don't know how many of the people who didn't get it learned from trying. So here we go. Here is how you analyze a circuit with Kirchhoff's current voltage law. Current law is the same thing. Current everywhere is the same. Now I don't have more than one resistor. Here is the voltage law. First, pick a path. I am going to walk around the circuit clockwise. You have to pick a direction as well. I'm going to walk around the circuit clockwise. And I'm going to analyze how voltage is changing as I go from each place to each place along that path. As I go around the complete path, my gains must equal my losses. But gains equals losses you have to consider the direction of the current and the direction of the batteries and the direction of the, oh my God, everything. Let's think about this. What I just say current does in resistors. Current wants to go which way? High to low or low to high? High to low voltage. Batteries, there's a choice. Well, it's not a choice, but I'll tell you that current sometimes flows negative to positive in batteries and sometimes flows positive to negative in batteries. If current is flowing negative to positive in the battery is supplying energy. Think about it. Current doesn't want to go towards positive. Current wants to go positive to negative. It takes energy from an external source, put lawyers on the upper floor of a building. It takes energy from an external source like a battery, put charges to higher voltages. If the battery is supplying that energy, current will go from negative to positive. When does the battery not supply energy to the circuit? When do you have a battery in a circuit where the battery isn't supplying energy? Huh? Well, then it's not in the circuit, the switch disconnects it. Have a battery charger. My laptop is plugged in, actually no, it's not. The iPad is plugged in right now. Its battery is being charged. Right? The battery is taking electrical energy and storing it as chemical form. That's what a battery charger does. It reverses the chemical reaction and turns products back into reactants. You guys have had more electrochemistry than I have, yeah? No? You've never had electrochemistry? Ever? Oh, what major are you guys? Medical studies? Forensic science? I thought they make you take 1 billion years of chemistry. No? Okay, anyway. Hold on, batteries don't go from positive to negative. When current goes from positive to negative in a battery, that battery is sinking energy. That's the direction that the battery doesn't want current to go. Batteries deliver energy when current is going from the negative to the positive. I don't know which direction the current is going in this battery or this battery. I know it's got to go either clockwise or counterclockwise. I have picked a direction to analyze that does not have to be the direction of the current. This is my analysis path. I now also have to pick a path for the current. I am going to guess. If I get it right, I'll get a positive I. If I guess wrong, I'll get a negative I. I'm going to guess. Come on, punk. I'm going to guess the direction of my current is going in the same direction as my analysis path. To the right in that resistor, obviously, if it goes to the right in this resistor, it will go down. This battery will go up. Yeah. So I'm guessing that current is flowing clockwise, and I'm going to analyze clockwise. Which side of this resistor is its positive side? Where's the higher voltage side of this resistor? Nope. Current likes to flow positive to negative. In a resistor, current always flows downhill. I have guessed that current is flowing right, therefore right is downhill. Which is the higher voltage side? Left. So this is the plus side of the resistor. Resistors don't actually have positive and negative sides, but I'm just going to indicate here. Oh, for God's sake, just going to indicate here that if this had a polarity, it would be positive to negative. Current is flowing from high to low. Current is flowing which way in this battery, up or down? Up. It's flowing to the right in that resistor, but it'd be flowing up this battery. Is it flowing the direction that batteries like to supply current? Or in the direction the batteries don't like to supply current? If a battery is doing what it wants to do It's trying to deliver electrical energy to the system. It's trying to boost electricity from low to high. If a resistor is doing what it wants to do, and it always does, the current is going to go from high back down to low. If current is flowing up in this battery, that battery is supplying energy to this circuit. Okay? Current is going down this battery. Is this battery sourcing or sinking energy? Current is going from plus to minus inside this battery. What did I say that? When did I say that happened? Sinking. This energy is this battery is absorbing energy. This battery is being recharged. If I'm right about the direction of the current. If the direction of the current turns out to be opposite, then everything is flipped. But I don't need to know. If I guess, I will work out, and then I will find out if if all those words need to be flipped at the end of the problem. Here we go. I'm going to write down my equation now. Voltage gain equals voltage loss. Let's step through each component. Have I gained or lost voltage from this point to this point? I've gone from negative side of the battery to positive side of the battery. Has my voltage gone up or down? Forget about energy, forget about anything. Which side of the battery is the positive side of the battery? Top or bottom? So have I gone up voltage or down voltage when I go from here to here? Up. Up. From negative side of the battery to the positive side of the battery. If I go from a negative floor to a positive floor, I've gone uphill. Okay. Is this battery releasing energy or storing energy? Releasing energy. It's driving charge where charge doesn't want to go. I'm assuming current is going up. It is delivering chemical energy to this current flowing through it. Okay. From this side to this side, the voltage is increasing. I've gone uphill. This is the voltage gain. As I go from the left side to the right side, do I go up voltage or down voltage? Down. I just wrote the voltage plus and minus here. I go from plus side, I go to the minus side, I'm going downhill. Does current want to go that way? Yeah. So is this a gain or a loss? Loss. Wait, hold on a second. Did I give you the number for this voltage? No, I gave you the resistance. How can I connect resistance to voltage? Ohms are 18. What's the voltage? Can anyone tell me the voltage across a resistor? IR, baby. That's what Burr means. Voltage equals current times resistance. If I've got the resistance of a resistor, I want the voltage of a resistor, V equals I times R. Anytime you have a resistor, you want the voltage across it, Ver. Why did I know I lost? If current is flowing to the right, I'm going downhill, going from high to low. That's a loss of voltage. Which side of the battery is the long side? Which side of the battery is the short side? If I go from plus to minus side, have I gained or lost? Done. Solve for I. What's I? Yeah, it's current, but solve for it. Give me a number. Nope. I've got an equation with one unknown. Take this and solve. Nope. Okay. Algebra time. I is unknown. I've got it multiplied by 18 and added to 6. What do I undo first? I get the 6 away. How do I remove a 6? If it's added to the rest of the equation, I need to subtract off both sides of the equation. 3 minus 6, what's that? Negative 3. 3 minus 6, not 6 minus 3, watch out. Negative 3 equals 18i. How is the 18 attached? So I need to remove it by, divide both sides by 18, what do you get? Watch your algebra, peoples. Algebra. Okay. Or negative 0.167 amps, whatever. Decimals, fractions are perfectly interchangeable for me.
I think that went the wrong way.
Yes. I guessed wrong. So the correct direction of current is from right to left in that resistor. Hey, which battery provides greater push, 6 or 3? Does it actually make some kind of sense that this guy is shoving current backwards through the 3 rather than the 3 overpowering the 6? Which side of this resistor is actually at the higher voltage? This side is actually the positive voltage, this side is actually the negative one. Does that make sense? If I say negative current is flowing right, negativity going right is the same thing as positivity going left. This isn't a wrong statement. You can say logically, it is true that I have negative 1/6 of an amp flowing right in the circuit. It's just most people would normally say 1/6 of an amp are flowing left in the circuit. Remember last semester when we talked about slowing down doesn't always mean deceleration. You can have a negative acceleration that speeds you up. Your velocity is negative. Same dealio here. You can have a negative rightward or a positive leftward. Those are equivalent. Those are logically equivalent. That's not a wrong answer. If I did ask you, just in words, which direction does the current flow? You should say leftward. You should assume I'm talking about positive numbers, leftward. But I do want to point out it's not illogical to write this number down. Okay. Turn to your neighbor, discuss the logic that went into this and how to solve. Very important. Hey, Sarah. Voltage. Okay, I got one more example. I hear a lot of productive discussions, but we do need to move on. You can't ask me a question though. Any questions before we move on to the last example? Yeah.
18 plus 6. Why did you create 18 down plus 6 on the top? Oh, you subtracted 6 here side. So I guess
18 times I plus 6 in PEMDAS. We multiply first and then we add. The 18 binds closer to the I than the plus 6. If I wanted this to be I times 18 plus 6, I would need parentheses. Good. Yeah. Uh-huh. Okay. I want to illustrate the node and the junction along. This time I'm not going to give you a complete circuit. I'm simply going to tell you that 2 amps flows into this harmony resistor combination. I'm going to tell you that half an amp is on the leftmost resistor. And I want you to find the resistance of the unknown resistor. I'm going to make the Kirchhoff node. It's more obvious here. Here's how to apply the laws. First off, let's name these. Instead of just I want to call this I1. This guy gets I2 worth of current. This guy gets I3 worth of current. Okay? What goes in current-wise must come out. What goes into this point? What goes out of this point? If 2 amps goes in, you can't have 3 amps come out. 2 amps goes in, 2 amps must come out. But where does that out current go? Here, here, and here. Do you see that I have 3 current arrows pointing away from this node? And 1 current arrow pointing towards that node? In equals out tells me the 2.0 amp current. Oh, for dog's sake. 2 amp current goes into 3 places, I1, I2, and I3. That's in equals out. What's the current in this wire? 2. Good. If I were just given the current down here, I could equivalent write in equals I1 plus I2 plus I3 equals 2 as out. Doesn't matter which is in, which is out, which is turned into sauerkraut. But out equals in equals out, just depends on which side of the circuit you look at. Wait, I have I1. I1 is additional information. I provided that as 0.5 amps. 2 equals 0.5 plus I2 plus I3. 1 equation and 2 unknowns. Can you solve that? 1 equation and 2 unknowns doesn't give you numbers. So I need more information. Fortunately, Herr Kirchhoff did not give off after one law. What was the other law? What goes up must come down, energy-wise. Let's voltage around this circuit and talk about the voltage gained and the voltage lost around the path. Okay? I'm going to pick without loss of generality. It doesn't matter, but let's pick that path for analyzing the voltages. Which direction does the current go in this resistor, up or down? Which direction does the current go in this resistor, up or down? Down for both, right? In this case, I'm going against the direction of current flow. Is it possible to analyze against the direction of current flow? Yes, absolutely. All I need to consider when I'm talking about gains equals losses, voltage-wise, gains equals losses is just a statement as have I gone uphill or have I gone downhill? If current is flowing down, is this the lower end of the resistor or is this the lower end of the resistor? If current is flowing downhill, is this the lower end of the resistor or is this the lower end of the resistor? This is. Current flows towards the lower voltage. Right? That's one of the basic principles we said at the beginning of class. Therefore, is this going to be a gain or a loss? I'm going from low voltage to high voltage. That's a gain. As I walk around the circuit, I've gone from low to high. This is a gain. That's equal from high to low. That's a loss. So what I could say mathematically along that left path is the voltage change what across the resistor is IR, I times R equals, that's the voltage gain, the voltage loss through the 15 ohm resistor. Yeah? Yeah, is good. Question? Yes. You pick any path that closes on itself, it's going to pass through two resistors. Those two resistors must have the same voltage. One you're going uphill, one you're going downhill. That's a general principle. It does not just depend on resistors. Voltages in parallel are always identical. Yeah. Right. Let's do the outer path. Okay, I'm going to start at the bottom of this resistor. Do I gain or lose as I go up the left? Gain. I'm going from its bottom to its top. I'm gaining. Go from top to bottom. Do I gain or lose voltage? Lose. That's right. Okay, so what's the equation that I would write? What's the IR for the left sucker? Oh, it's the same as what I just wrote. What's the IR for the right sucker? Yeah? Make you sensey? Now I have three equations and three unknowns. I don't know I2, I don't know I3, I don't know R. But using the great and powerful principles of algebra, I can solve for these. Let's take this equation. This gives me I2. What's I2? One third, yeah, you see that? 0.5 times 10 also goes by the name of 5. 5 over 15 is a third. I2 equals 0.33 amperes. Okay, now equation 1 tells me 2 equals 0.5 plus 0.3. What's that mean? 1.17? Is that it? Do y'all see where I'm getting that from? Plugging into number 1? Yeah, absolutely. If I take I2's value here and shove him up there, I have 2 equals 0.5 plus 0.33 plus I3. How do I get I3? Now I've got I2, I've got I3, and I've got one final equation. Left-hand side is 5, right-hand side is 1.17 R. What's R? $4.3, is it? I can't do that in my head. Units? R. Oh. Can't have piratism without meditation. Piracy, piracy. Real fast, turn to your neighbor, discuss how do these illustrate the Kirchhoff laws, restate the Kirchhoff laws, and then you can go. Or ask me questions. You now know everything you need to do to complete the homework and the quiz. You are free to leave or ask me questions. You know, resistor charge always goes in parallel. But a battery really wants to. But it will, I won't say it's but it just push. But that's not, you can reverse the direction of current through a battery. That just recharges the battery. If it's recharged.